Time for another DraftScience video presentation. So we'll just go over the facts again, what I propose to be well-stated, semi-decently articulate descriptions of the current state of things in terms of what can be understood to be the truth, mostly factual, and with different emphasis, I suppose, how much strength we could say a certain fact has been established, how much corroborating evidence there is, what the evidence is, frankly. What won't be in the list is, entanglement and all kinds of other crap that really hasn't been established with any kind of volume of evidence. So anyway, yeah, and so this week has been interesting. A couple of new facts, okay, reasons, and so I figure I can add something to the reasoning to make that understood. I had to understand it, so I'll explain how I understand it. Okay. So, number one hasn't changed any. The single slit math models two vectors with point sources at the surfaces. Okay, that is, the math models two diffracting waves with their centers at the surface. Says. Okay, so this is pretty well established that the idea, this just has to do with path length difference. And even if you have a Huygens theory that there's an infinite number of little wavelets being created, the truth is they all cancel out, and for the purpose of doing the mathematics, all that matters is what is this distance and how many wavelengths fit in it. How many marks could you make inside of there constituting a full wavelength, and so you get some sort of number like 15.5 or some kind of number, and that number will tell you that if you have one length of distance, L, okay, so perpendicular from one of the two sources, leave that a perpendicular, say that's your L, and then you're just going to say, you're going to take this other line and say its distance can change, and then you're just going to find points, okay, where you connect the two and you see, did this one get bigger by a full wavelength? And if it didn't, then you're still offing. And when you get to the point where you have a full wavelength of difference in this line, some point over here presumably, so this line stays the same, L, that's why it's a curved surface, and this length can change, and that's called the path length difference. Okay, so people are using this acronym, path length difference, a PLD. Woo! And that's all the math is representing. So the math is just representing what would happen to these two vectors. So whether you're doing the math by bisecting this with a normal line, and then taking this line going this way, and then taking this line as being a right angle, and then taking this sine theta, and blah, blah, blah. It doesn't matter how you're doing it. No matter how you're doing it, you're doing the same thing. You're just saying, when is this line a full wavelength longer than this line? And that's it. Well, we'll get to that part later, the in-between part. But so that's all the statement's saying, is that everybody sort of agrees. It's not really contestable in any way, but that's what the math is doing. Everybody's math. All the math. Pretty much. There's not some other model of what's actually happening. That model explains why the colors separate. The model explains a lot of things. So it works as a model. That math works. Okay, number two. The math predicts models. So again, math is for the purpose of modeling in an abstract world. That's what mathematics does. It takes the reality and it's modeling it in an abstract way using numbers, vectors, to just kind of indicate what things are, reducing them to very simple, basic elements. And the intent is to get all of the variables that matter into your math. That's the intent. And the point is it working? I would argue for the purpose of the slit experiment, the single slit, it works to understand, yes, there's distances that matter, the distance between the two sources, the focuses, and the distance that you want to view it at matters. And so those are elements you need, and then the wavelength of the light. Those are your three variables that have significance, and there really isn't any other variable that makes any difference. Alright, the math predicts models a result on a curved surface of radius L. So I just sort of illustrated that. I probably shouldn't have to do it again. Okay, that the whole point of the math is to find the difference in a line that's the same, okay, a vector that doesn't change, and a vector that does change. Now with the string experiment, you're changing the vector indirectly based on the length of this, but this doesn't vary, so it doesn't really matter. So it does work, but the idea is yeah, it still works, but I'm just saying to keep it simple. The simple argument is that you're comparing a constant, the length of this line, with something that's not constant, the length of the other line that has to cross over into the other focus's world. So these two focuses have two different worlds. This one's right angle is here, this one's right angle is here. You're taking this focus and projecting it into the world of this focus, okay? And it changes length based on the fact that it's traveling into the realm of the other point source. That's one way of looking at it. I'm just saying, understand, one is fixed. I don't know how to draw a fixed line, fixed length, and the other one is not. And all you're doing is comparing the length of those two lines. I might as well do it now, since it's on my mind. So the way I'm understanding why there's a difference in the size of the nodes, so the places where you will find the place where there is a wavelength of difference. Now, at the focus in the center, where the two are inside of 1 millimeter, we'll get to that subject, okay? That's not a wavelength difference. They're the same length. So it's not really a wavelength difference. But it's the same thing in the sense it's not, one line isn't longer than the other by some portion of a wavelength. So anyway, but the first real wavelength difference is probably going to be someplace like here, let's just say. And then the next node would be here. Well, I should draw these really close together because that's the point I'm trying to illustrate. So what's going to happen is you're going to get a constructive that are fairly close together, and they get further and further apart, which means they also get bigger and bigger in terms of what you see visually. So obviously the nodes are bigger than the center. The light isn't just in this one tiny spot, it spreads across what you could call a node. And that node of bright gets smaller and smaller as you go up towards the top here. Now, the way I'm understanding why that happens is to understand what happens when you're increasing you know, a base and a hypotenuse. So you could say you have a base, and then you have a standard L line, and then you have this new line, which is that's this other side that's getting longer. And it gets longer because you're basically just changing this position. You're changing this from a line going this way to a line going that way, or vice versa if you have it pointing up this way. You're just changing, okay, this base, okay, and then this is your line that's going to get longer. And what you're doing is just moving the angle that you can see it at, and that's the same thing as just understanding that you're moving it from being here to being up here in terms of how somebody's viewing it. And so you can understand that when it starts off, it's got a high portion in this direction, in the sense there's lots of change, and then it's doing all its changing in this direction, right? So that's basically what you're seeing here, is that there's a lot of change when it first starts moving out, right? When I first start bending this line, there's lots of change. Okay, a tiny bit of difference makes a big difference in the length of the line. I mean, obviously that's it. This, that's why I did it this way. Okay, it's because there's a tiny bit of change. As you first start to move the line up, you're creating a lot of change, and then as it normalizes in the sense of changes direction. So you can see there's two different directions there, right? There's up, and then there's across. Obviously, when it's moving in the direction of the length of the line, it's creating a lot of change with a little bit of movement. But when it's moving this way, it's not creating much change in that direction. So that's all you have to understand, is when you lift it, it moves on an arc, and that arc is just being reflected over here, in the sense that you start off making lots of changes in the same direction, and then your changes start changing, okay, which means you're going the wrong way, and you have to travel a lot more distance to create any wavelength. To add to the length of the line, you have to go a lot more distance to create any effect, because you're going mostly this way and very little this way, right? Where we're here, you're going mostly this way and very little that way. That's the simple way to that's how I understand it. So anyway, not that I said that perfectly either, but it doesn't matter. So I don't think this is a disputable fact that if you're going to do the math and figure out where the nodes are, you do have to keep the line, that L, the same distance. Now the vector, the point at which there will be constructive and destructive interference, is always, it's going to be a straightish line. I don't think it's going to be straight. It might actually be a parabola, as Professor Lewin says. But regardless, so you could go to different distances, but it's not constructive to understanding the proportions. You're going to get the sizes of the nodes wrong and everything else, because the further out you go, the more they're enlarged. So you won't get the positions right unless you're just using an angle. So unless you're doing a specific kind of math dependent on angles, you're not going to be able to get the right answer by changing the L distance, the distance from the target. So, yeah. Alright, the number of possible nodes, locations of constructive or destructive interference, is defined by how many wavelengths of light fit in the distance between the surfaces. So the distance, the reason why it's relevant is because of how many wavelengths fit in it. And that number will be reflected in a pair of nodes being created. Obviously there's two things being created, the on and the off. So there'll be the same number of pairs of an on and an off, okay, as there are frequencies in here, wavelengths. Seems pretty logical. Alright, dividing the wavelength into the distance between the surfaces will tell you exactly how many on-off nodes. So that's, I guess I'll say pair of on-off nodes. So we just put the word pair of on-off nodes you will be projected onto the surface. So not a hard reach. There seems to be an obvious relationship. That's why the math works, is because there's kind of a definite relationship between how big the path length can be, how long the line can get, how many wavelengths of distance increase you can have, how many times you can go a wavelength further, has to sort of be dependent on how many wavelengths are in that base. Alright, so nothing here that I think a reasonable person could disagree with, but whatever. The path length difference at 90 degrees, or 0, depending on your want to play the game. So I call this 90 degrees, but frankly, perceptually wise, right, it's probably better to use 90 degrees here, because that's more traditional in terms of understanding your right triangles and all that kind of stuff. But that's semantics. Okay. is the total difference between the surface and dictates what the node at 0 degrees will be. The nodes are equally sized. So that little piece of crap goes, because that's not true. So that's what's changed, okay, is what was in the parentheses. It's unnecessary. Again, it was argued merely as a way of making it easier to calculate. If you wanted to know where a node was, all you had to do was, once you knew one node, you'd know all the nodes because they were equally sized. Well, if they're not equally sized, then you don't know all of them. Unless you know at what rate they got bigger and smaller, and you know exactly which one you're looking at. So that doesn't work. Alright, so, but this is a simple argument that both places, the 0 degree and the 90 degrees, dictate each other, and they also are dictating. They're being decided by the other, and they are deciding the other. So, you know, there's a push-pull thing. So you can make the simple argument that if you have one length, okay, that's L, and then the other length when they're going exactly in the same direction, you can understand the other line is going to just be the distance between the surfaces. That's how much longer it's going to be. So if there's 15.5 wavelengths in that distance, this one's going to be 15.5 longer, and 15.5 would be an off. So we would know this is an off. And if it was an even, a whole number, then we know it's an on. So that's pretty simple, right? That's not, that's a pretty simple answer. A way to say we know what this one is, okay? And then the same thing is happening at the top, in the sense that you're just taking this, okay, this is the L, the one that doesn't change, and you're just saying this is where your right angle is, and you're saying there's a line that goes from here to here, and you know what that one's going to be. So you know what this hypotenuse is going to be because you know what this distance is. And what this distance is going to dictate what this position will be. Okay, so that's it won't be the same as just adding 15. It'll be the same as squaring the sides and, you know, doing your Pythagorean figuring. But the point is I just changed this number, and I changed this position from an on to an off. So there will be numbers. Okay, now they're not going to be whole numbers here because of the hypotenuse is changing proportional to this base size, not directly. So this one is direct, this one it's an indirect increase. Okay, but the fact is if I change this number, I'll change this from off to on, kind of idea. The actual position will be somewhere like here for a true on. So it'll become degrees of off. Let's see, we could say that, based on this difference. You know, so I changed this distance, I changed this distance, obviously this single point would change in distance. So it makes you know that this is not an on node, right? This is the on node. The center of the pattern is going to be this size, and we're talking about positions inside of that. And what the geometry insists is true is that this little mark in the middle where the two lines would meet, where I could do this, is tiny, and that's a definite on all the time. But this spot, just a 1 millimeter next to it, isn't a definite on. It's actually more likely to be an off. And it doesn't get to be a full on until it gets somewhere like here or here, you know, on the two sides. So this really is just two nodes, okay, that just happen to be, you know, merged. The geometry insists that it's sort of true. There's no way to get around this simple geometry, that this is inside of 1 millimeter. This can't spread out. Two converging lines on a focus can't possibly make something bigger. You know, can't do it. They can't go over here and make a photon. They can't go over here and make a photon. Those two lines can't do that. So, you know, it's sort of obvious that this is kind of a moot piece of information. These two lines going the same way inside of 1 millimeter are not really relevant to what the pattern is. The part that's creating the pattern are the two lines going in the same direction. And obviously that focus, that first node where there's a wavelength of difference. See, here there's no wavelength of difference. They're the same length. So when they're doing this in the center, they're the same length. And you don't get a full increase in the length until some point here. Some point off that center. So the center can't possibly be an on because it takes a time to get to a full wavelength of difference. So we know the center for the first real node has to be here, in this, you know, here, and those are the real centers. And all that's happened is the two nodes are merged. So that's saying more than's in this writing, but that's the idea. That's hard to describe in words, so I didn't put those words in yet. But I'll work on that. It's in words, but it's not in words that say it is, you know, and with as many words. Sometimes you have to use more words. All right, the number of the surfaces dividing the wavelength. Yeah, that looks like a note. Into the distance of the surface, tell you exactly how many on-off nodes are projected onto the curved surface. So that one we already established. The path length difference at 90 degrees. So that's 90 degrees, you know it. Really easy. That's the easiest one to calculate. And then this one, you know it can't be an on because it can't be a path length difference in the dead center. So you know that can't be truly an on, right? You kind of know it has to be an off because there can't be a path length difference. That is a wavelength, a whole wavelength difference in the distance can't exist when the two lines are the same length. So obviously that can't be an on. All right. Even though the little lines are saying it is, even though the little tiny diffraction inside of 1 millimeter says on, the real pattern says off. Okay. It's sort of an important point. Anyway, the equidistant vectors pointing to the center, okay, so that's these that I'm talking about inside of that tiny space, do not create real nodes. They obviously can't create a node that might be 5 centimeters across. They're inside of 1 millimeter. They can't obviously be 5 centimeters. As they only span a tiny distance, the distance between the two surfaces at the target. So they don't even span the distance of the two point sources. They're really smaller than that. It's something smaller than in between the two sources. Real vectors move in the same left-right direction. So the real vectors are created by two lines going the same way. That's how you get the path length difference. You have to create the true hypotenuse. See, two lines going equidistant, they're both can't be hypotenuses. There's no hypotenuse. So therefore there's no path length difference. Okay, I'm going to pause for a second because the voice is old for, at the moment, not functioning. Alright, that wasn't too long. Anyway, so, alright, the equidistant vector, I did that. Alright, the experiment is easily modeled with 2L length of string. Okay, so we're not going to bother with that anymore. Attached to the point sources are marked in wavelength increments. Because it doesn't really model it. Well, I can't even say that. Frankly, well anyway, this is suspect. I don't think there's any point in using it anymore. Because it does give you different results depending on how far in and out you go. I'm think. See, I'm just saying if I just make it a wavelength of string, you know, one wavelength, it's not going to give me the right answers. But anyway, I just, yes, we can do without it. Since it causes some confusion now, rather than making anything clearer, that'll probably just get deleted. It is superfluous. It's unnecessary. You don't need to know any more than the simple idea that you're just saying how much longer is that line getting. And when it's a full wavelength, I know I have the center of a photon node, one that's on. So we don't need this anymore. Alright, so we'll get rid of it just because it's just getting in the way. Alright, so the double slit. So now we've figured out the mechanism that path length difference is all that really matters. That's what we're deciding, and how many path length differences there can be, how many times you can go a full wavelength of rotation in the length of the hypotenuse. Okay, there's only a certain number of those. Then the double slit is just really breaks down to just being two single slit experiments merged. So I've done this so many times, but I'll say it first, right? The double slit experiment is just two single slit experiments superimposed on top of each other. So it's not this opening and this opening. It's not this distance and that distance that we're merging. When you're merging the two, you're creating a new distances. You're creating the distance between these two surfaces and the distance between these two surfaces. That's what you're merging. So you're not merging this D plus this D. Those are the same D's, right? So it would just be D1 would be 5 and D2 would be 5. That wouldn't get you anything. What you're merging is this D, which is going to be a number. If it was 5, you know that D2, this distance to this distance, is going to be 10 or some other number bigger than 5. Alright. So not a single slit of the same dimensions, but rather a composite product of a single slit with the dimensions of the center, and you know, the impediment, and a single slit with the dimensions of the outside surfaces. So all you're doing is saying, no matter how many slits you have, you're really just saying what's the two surfaces that are the furthest away. And you take that and you make that one experiment. Then you take the surfaces that are the second furthest away, and then the third furthest away, and then the fourth, and you just keep doing that. So as I have illustrated in other videos, you could have multiple slits, surfaces, alright, and all you're really going to do with any number of surfaces, whether it's one or a bunch of surfaces, you're just going to say, what's the two furthest away? Okay, that's these two, right? So I'm going to take those two and say, that distance, how many wavelengths are in it? Well, how many wavelengths are in it? The more wavelengths, the more points at which I can have one of those light things being created. I have a wavelength of difference in the hypotenuse. So the more number of wavelengths that fit in here, the more notches it creates on the same length of surface. So basically, the two outside surfaces are creating little bars. And then these two, since it's smaller, has fewer wavelengths, it creates a little bigger bar. Alright. And then these two, because it's a smaller distance, it creates an even bigger bar. And what you're ending up with is a pattern of these bars right on top of each other. And when all of them line up, that's an on. Okay, for the experiment. You've sent pieces to all these locations and all of them are in phase. Now what happens as you go is that the phase is broken here, where now they're not lined up. I mean, I should make the darkers bigger so you get the idea that you're competing with the dark space, right? So it's not drawn very well, but the idea is they all are creating dark spaces next to them, and the point is now they don't line up. Now when you go through, this one's on, this one's off, this one's off, this one's on, you know, you're not getting all of them on, all of them in phase. But you will recreate this perfect pattern again, it'll reoccur right out here, and it'll reoccur right out here. So it will, this alignment will show up again, and then again, and again, and again. Because it is a resonant harmonic oscillation, essentially. It could be described as one, it could be modeled as one. And so that's why this works for the single slit, the double slit, the triple slit. Doesn't matter how many slits you have, the concept of them all having to be in alignment, they all four sources, so to speak, in the double slit, the four sources having to be in phase for you to get a very bright. Yeah, I think that's yeah, I think that says enough about that part. The double experiment is just two single slits, so that part I'll draw now. Yeah, so let's just do that real quick, and that's all there is. So it's very simple. So there's no real math except understanding the math of the single slit. And you're just saying, I'm going to combine single slit experiments, and where they agree with each other, where their pattern overlays with on, is where there's likely to be a photon, and where they're not in alignment or not in phase, there won't be a photon. And it's pretty much that simple. So the idea is you have two slit experiments, or two impediment experiments. You can do two obstacles too, because two obstacles create the same surfaces, right? I mean, a single impediment, like a needle, creates the same idea as two surfaces. So it doesn't matter whether I'm combining two single slits or I'm combining an impediment and a slit. So same difference, or two impediments. And the idea is to understand is these have distances when you start. Well, this is the only distance involved, that distance between these two. This distance, the distance between these two. And what you really should be seeing is when you're combining them, you're creating this new distance of the impediment you're creating. Now you have this distance, which is now new. It's not this distance, it's not that distance. And then of course you have this distance of the outside that you're bringing in, and that distance is a new distance that you've created by merging the two. So you're really doing two experiments, you're just superimposing them. You're doing the single impediment experiment here and saying what's the pattern it created, and then you're doing a wide opening experiment here and saying what's the pattern it created, and you're just putting the two patterns on top of each other, and where both patterns are on is where you get ons, and where they're off, where one of them's in phase and the other one's not, the sources, you're out of luck. So that's what creates the classic envelope pattern of the double slit experiment. This is usually an odd number, says some people. Okay, so let's put an odd number in the middle. Doot, 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 doot. Okay, so you have this obvious break, and the obvious break actually in some experiments you can actually see it's still there, it's just very dim, you know. So you can just see that you're getting you have two patterns. You have the envelope pattern that's saying make these brighter, and then you have the little bar pattern where, oh, I'm not consistent with the envelope. The envelope is sending photons here, and sending photons here, and sending photons here, pieces. But it's not sending any here, so, you know, the one pattern is the only light for those. So this one has 2x or 4x the brightness of this one. That kind of idea. Because you're just combining. Sorry, that's not very visible. Short light for some reason. Yeah, we're a little, there's really plenty of light. Might be the chalk. I don't know. I'll figure it out later. After the video. Yeah, yeah. It's always best to do it after the video. Alright, so I think that's all that needs to be said, right? I don't think there's any other feature that needs to be described or explained about the experiment. If there is, please include the suggestion below if there's some aspect that you think needs to be explained. Some basic feature of what happens when you have these surfaces interact. But I just don't think there's anything wrong in what's stated. It might be incomplete, but it's certainly not wrong. Okay, so that's enough of a video, I think. So, there's people who make, response, I'll just say, Stephen Broke, if you can't make a reasonable video, I'm not wasting more time watching videos that are contentless. I mean, he keeps making claims for which he has no evidence, and that's just a waste of time. So that's just like the Hillster saying the earth is getting bigger. Yeah, show me it getting bigger. Till then, that's just talk, and so all he's doing is talking out of his, it's just a waste of time. So, yeah, I'm not going to respond to nonsense. Stay on the subject, or do something like fall into some sort of substance that makes it difficult for you to make videos and do other things. Anyway, it's too stupid. Just such a waste of time. So, this has been a DraftScience video presentation, and until somebody can show up, I mean, it'd be nice if people could actually talk about physics, but apparently it can't be done in some sort of ordered, sensible manner. Like, even if you disagree, you just move on to the next subject. You just say, okay, well, see, me and Franklin, we're talking about subjects, and he has a completely different theory. I can't overwhelmingly prove mine to him, and he can't prove his to mine because I see flaws in it. So you just have to move on to another subject until you find the evidence to be able to point. So it's like there's a disagreement about whether kinetic energy is conserved or whether momentum is conserved in the real universe. There's a right answer. Everybody seems to be on one side in some sense, in the sense of saying kinetic energy is conserved. I mean, momentum. You can't do anything to break that basic rule. Third law, Newton's third law, and all that kind of stuff. But there's this counter argument, and that should be argued out. And instead, nobody argues, and they just say, well, let's just believe in both. I mean, photons really are either waves in something, or they're not waving. That is, the elements of the photon are not interconnected in some way, and they don't stretch and change shape and morph and do all kinds of weird things. They're either bullets at a frequency, or they're dominoes falling in some kind of bizarre manner. I don't know. I don't even know how to describe the medium of their ethers. But anyway, there's a truth, and apparently people aren't that interested in finding it in some sort of certain way. I mean, I'm quite certain, so, for me, there's plenty of evidence indicating wave theory doesn't work. But, it doesn't help not to have the conversation. But they can't have the conversation without being, without threatening my, personal security and the security of other people who live by me. They have to threaten them. Pathetic. So anyway, till the next time and such. Yeah, this is just, kind of funny. I cut myself off. I was going to, I was saying some more stuff again where I didn't end the video, but I did hit the button. But anyway, so we'll do it again just for fun. Anyway, so this has been a DraftScience video presentation. Thank you for your attention. Blah, blah, blah. Goodbye.